Hi guys! So here is part 2 of our lecture for week 13. And I want to start by showing you guys the formulas that we've covered so far. We had the Biot-Savart law to calculate the magnetic fields using a partial segment of the wire, just like KdQ over R squared when we did the electric fields. We had Ampere's law, which stated that along a path B times the length of the path is equal to mu0 times I enclosed, and this has to be a closed path and enclose some currents. Otherwise, that would mean that this path integral is 0. And this was similar to Gauss's law in electric fields. And the reason behind a magnetic field was moving charges, and something we could calculate was the B field created by currents. So that's why we had these two formulae. And we could switch between charge and current using I equals dq over dt. And all the moving charges, including charges in the current, are affected by magnetic fields, and we had two magnetic forces, qv cross b on a single charge, il cross b on a current carrying wire. It also had this integral form, idl cross b, which is a formula that we use when either B field is not uniform on the wire, it changes with dimensions or distance, or if we had like a variable angle, non-uniform angle between the L and B, or even when the angle is uniform, we would have a non-uniform direction for the force for each segment dl. That's when we have to use this integral form. On our formula sheet, on top of these formulas, you will also find the B field formulas. B equals mu0 I over 2 pi r, the B field created by a straight current carrying wire, an almost infinite one. You would also find the formula for a ring charge at the center of the ring, mu0 I over 2r. And remember, last lecture we calculated, or in part 1 we calculated magnetic field of a solenoid mu0 Ni. You can also find these formulas in the formula sheet, and you can readily use them if you must. We also learned so far various right-hand rules, and I will go over them really quick. One right-hand rule was to calculate the resultant force in a cross product. This could be F equals QV cross B, F equals IL cross B, or to calculate the direction of ds cross r hat in the Biot-Savart law. You had curling of your fingers, fold V on top of the second vector B, your thumb would show the direction of the resultant vector F, or you could use your thumb to be the first vector in the cross product, your fingers to be the second vector on the cross product, your palm would show the direction of the third and the resultant vector. We also had right-hand rules to calculate or to find the direction of the B fields, magnetic fields. If you have a current carrying wire that is straight, then you put your thumb along the direction of the current, and your fingers make a circle around your thumb. They are curling around your thumb, showing the direction of the B field along this direction. So this blue circle would represent the direction of B field, and if you wanted to calculate B field at a certain point on this plane, let's say at this point, you would have to draw a tangent to the circle to find the local magnetic field direction. Let's say at this point we have a B2. Let's say at this point, tangent to the line, we have a B3. So we utilize our fingers to find these little local magnetic field directions. The third right-hand rule method involved finding magnetic fields for curling currents. We can use this for a ring or for a solenoid. If you put your fingers towards the direction of the current, which curls, your B field is on a straight line, and your thumb shows the direction of the B field, this way in this case. So we have three different right-hand rules, one to find cross product and the other to find the direction of B field. So A ring current creates a magnetic field at its center. And it does that just like a bar magnet. Okay, so we have a parameter called a dipole moment, which is just the current times the area of the loop ring to represent this loop as a magnet on its own. Okay, so each current carrying loop is a magnet and it has a dipole moment, which is its current times its area. Well, we want to utilize this mu vector, which is the direction of the area vector, but you can say, hey, this is a circle and its area vector can be either up or down, normal to the plane of the ring, but it has a preferred direction to find the magnetic dipole moment direction. Again, since current is making curl, you curl your fingers around the ring, your thumb shows the direction of the field created by the ring and the dipole moment. Remember in class, we had this example where we calculated total magnetic force on a loop of wire. This itself is a magnetic dipole. It has a dipole moment. If you curl your fingers towards the direction of this current, the dipole moment goes out of the page, and it has a magnitude I times L squared, since it has an area of L squared. We calculated the total force acting on this loop of wire. Each segment had an individual force vector acting on it that was towards in to the square, inwards direction. And each of these sides facing each other, the force cancelled one another and we had a net force of 0. Well, even though this was a particular result of this problem, for every loop, if the loop itself, all of the loop, is in the magnetic field, this result can be generalized for any loop of wire. Total magnetic force acting on a loop in a magnetic field is always 0, because the little segments facing one another, even if it's a circle or a square or a rectangle, will cancel each other off and you'll get a net force of 0. But net force being 0 is a good thing from an engineering point of view, and there is one parameter that's not 0 acting on a loop of wire. And these two are utilized in our daily lives very efficiently, let me say. So let's look at this example. Wire of loop in a magnetic field. This time we're putting this square in a magnetic field that is towards the right. We're putting it kind of going into the page, so we're kind of looking at it from the side. And this loop is held there by these little pivot points. Okay, so it can easily rotate around this axis that goes into the page. Okay, so if we again wanted to calculate the net force acting on this loop, it would again be 0, since all of the loop is immersed in the field. And these would be the current individual force directions, and they will cancel each other out. F1 would cancel F2, F3 would cancel F4. We would get a 0 net force. But as I told you, there's something that is not 0, and we'll utilize that. Let's look at it from the side view. So we said that this loop goes into the page or into the board. So looking at it from the side view, current comes out this way and goes in that way. And on this side, it goes down, goes in, comes back out that way. So we have this loop we're looking at from the side view in the magnetic field. Again, the net force acting on it is 0. And here are the two forces that we can really see. The ones acting on the top segment and the bottom segment. So here is the pivot point. Please make sure you know this word, pivot point. Pivot point is a point around which your object can rotate. Okay? We said that there is something that's not going to be 0. Let's tilt this loop in the magnetic field. See what happens. The net force is still 0. These forces still exist, and there's still, one is upwards, one is downwards. Okay? Let's say we rotated it at an angle theta, so that this plane of the loop is making an angle theta with the normal to the B field. Alright? We want to calculate a parameter called the torque. Remember from Physics 101, torque is distance to the pivot point times the force, but it's the cross product of these two vectors. So even though F net is 0, each one of these forces will create a torque. And here, the vector that I drew here is our dipole moment for the loop. Here is our dipole moment vector. Because I want to rewrite this torque formula in terms of the dipole moment. So each one of these vectors, F1 and F2, will exert a torque on this loop. And since it can freely rotate around this point, it will rotate eventually. So we can write the individual torque vectors created by F1 and F2 depending on this angle theta that we started out with. R cross F. So this is the distance from the pivot point to the force, which is half of the length here, L over 2, force F1, and the sine of the angle in between. This I hat vector is actually a vector that is pointing out of the page. So the torque vector for the first one is pointing out of the page, which actually, if you use your right hand to show the direction of this I hat, your fingers will show the direction of rotation, which is going counterclockwise in this case. And for F2, the same thing will apply. L over 2 is R, the length, force, and sine of the angle in between. Here is our axis. So, since F1 and F2 are the same magnitude, IL times B, and these two vectors are pointing towards the same direction, they add up to L over 2 plus L over 2 is L, ILB for the force, times sine of theta. To rewrite that, it's I L square B sine theta. Replacing L square with the area, it is I times A times B times sine of theta is a torque. Well, I times A was the magnetic moment, and this is just like the cross product of two vectors because this theta is actually the angle between mu and B as well. So this angle is actually alpha 90 minus theta, which is also this angle, alpha. So here, angle between mu and B is also theta. So this formula is just like the cross product of mu and B. So torque equals mu cross B. Torque acting on a loop with a dipole moment mu is mu cross B. And this torque will rotate this loop in a counterclockwise direction since torque is along this x-axis. Alright? So we calculated the torque. Mu cross B. Well, what happens? What happens is this. This loop will rotate along these directions the arrows are showing. And as you can see, the torque created by F1 is not opposing torque created by F2. They're actually rotating the same way. That's how the vectors added up. And eventually, this loop will align its magnetic moment, mu, with the field. So mu will align with the field. Well, will it stop there? Well, eventually, yes. The loop will stop at this particular position. But since it would have an initial speed, it will cross over to the other side. This time, the torque vector will switch its direction, trying to move the loop. This end going this way in a clockwise direction, this end also in a clockwise direction. So the torque will switch its direction towards minus x once the loop passes over to the other side. And as you can see, the torque is again trying to align mu with B. It will rotate and come to an all straight position. So actually it will oscillate and eventually stop aligning with the field. And this is going to be the final position. Let's see another example. I wanted to give you guys this for an example. See if you guys really understand what you read, which is very important during an exam. So here is a question without any figures. I want you guys to picture what the question is saying. So let's read it together. And please take your pen and paper. try to draw what the question is asking. And I will pop the picture up after I let you draw the picture. Current carrying wire with magnetic dipole mu directed into the plane lies on the plane of the board in a magnetic field that is towards out of the board. Okay, did we understand that? Rereading, please take note. We have various directions, like 3 different directions here. We have a current carrying wire with a magnetic dipole mu. How is mu directed? Mu is directed into the plane. And this wire loop, it has to be a loop because it's a magnetic dipole, lies on the plane of the board. Okay, so we have a loop lying on the plane of the board. Its magnetic dipole moment is directed into the page. And it is sitting in a magnetic field that is towards out of the page. So can you draw me 1, the loop, 2, the magnetic field direction, and 3, the dipole moment direction? Now you have to draw me a clear picture with this explanation. All right. Okay. See if your picture looks like this. We should have the same picture. Magnetic field lines coming out of the board or page. We have a loop on the plane of the page. Okay. It can be circular, square, it doesn't matter. Since they just gave us a magnetic dipole moment, I drew a circle. And its magnetic moment is towards into the plane. So if I put my thumb into the plane, my fingers will be curling clockwise. So that's how the current should go in this loop. Okay. So, continuing the question, see what we understand from the question. We tilt the loop towards into the board, an angle pi/4 around the horizontal axis. How does the loop rotate? Since the question says that we can tilt the loop around the horizontal axis, this is where the pivot points should be, rotating freely around this horizontal axis. We're tilting this end into the board. So once we do that, we actually get an angle of pi/4 between mu and b. In its initial state, till here, in its initial state, we cannot talk about any torque whatsoever. Why? Because remember, torque was mu cross b. And mu and b are aligned. Actually, the angle in between is mu times b times sine of. One is pointing into the page, the other one is pointing out of the page. The angle in between is 180 degrees. So as the first part of the question is concerned, there's no torque on this loop. But there will be a torque once we tilt this end of the loop towards into the plane. Alright? And this loop will rotate. How will it rotate? I'm giving you a second to think. Give me an answer. How will this loop rotate if I push this end towards into the page? Okay, I hope you have an answer by now. Well, you could calculate mu cross b and see what the torque direction is like. What you could also say is that mu will want to align with b, right? Let's look at it from the side. Looking from the side, looking from this side, right? Here is a loop. We have a b going that way out of the page. We have a mu pointing into the page, and we're tilting it. We're tilting mu this way. Let's call it mu prime. So once we tilt it this way, let's calculate the vector mu cross b, right? if we do mu cross B, our thumb will show towards into the plane, right? So this torque will want to rotate it. If you put your thumb towards mu cross B, it's like you're folding mu on top of B. So once you push this end into the plane a little bit, this mu will want to go all the way and come align with B. So this loop, if you push this end in to the field, it will go all the way around, come back out this way, making mu finally align with the B field. That's how it's going to rotate. Okay, the sound will go in, come back out, so mu will eventually change its direction to towards out of the plane. Well, this idea is actually utilized in an electric motor, but as I told you before, like in this example, if we had mu aligned this way with the B field, it would want to make it rotate clockwise. If the stick was on this towards this side, the loop was tilted towards this way. When it was tilted towards this way, it wanted to make it rotate that way, always trying to align mu with B. So I'm telling you that this idea, we want to utilize it in an electric motor. We don't want to just oscillate this loop. We want this loop to cross over to this side without feeling this torque. We want it to feel this torque and keep rotating, make a full circle, so we can utilize it as an electric motor, use it anywhere we can think of. Trying to make fans for our hair dryers, use it in a car to make the car go forwards rather than forward, backward, forward, backward, forward, backward, right? So we want to make this loop go in a circle rather than oscillate back and forth, back and forth. Okay? How do we do that? Come on, engineers. You guys were smart enough to come up with an idea to make this loop go all the way around. This is what an electric motor, a DC motor, looks like. You guys came up with a beautiful, ingenious idea to make this loop go all the way around constantly. Well, looking at this figure, maybe you can't figure it out. But what do we have here? We have coils. Here is a coil. Here are two coils. These are the magnets, the red ones. So you have coils sitting in a magnetic field that is towards this direction, in a horizontal direction. Okay. And here we have positive and negative ends of our DC motor. So we connect a battery to this. We have a loop of wire, current carrying loop, magnetic dipole in a magnetic field. Why do we have coils here instead of a single loop? Well, the more coils you have, the more torque you will feel, because it's going to be N times R cross F, or N times mu cross B. So you will get a bigger torque. Well, here. So you have the magnets at the sides. Instead of looking at a coil, let's look at a single loop. Here is a single loop, okay, connected to these metal electrodes, which are half circles. Metal electrodes that are half circles. And these electrodes are touching the ends of a battery, okay. So let's say this is the plus end of, connected to the plus end of our battery, and this is connected to the minus end of our battery. In this configuration, you would have a current going that way in the loop. Here's the dipole moment of this loop, right? Pointing upwards. And magnetic field is pointing along the horizontal direction. There's a 90-degree angle in between mu and B. So this magnetic field will want to rotate this loop this way, along the direction of the arrow. Let's see what happens when we rotate the loop. These electrodes will rotate along with the loop. Now, still this end of my loop is touching to the plus end of my battery, and this end is still touching at the negative end of my battery. As I start moving the loop, or as the loop starts to rotate itself under the effect of this torque mu cross B, this end will go up, and eventually, right when my mu is going to align with my B field, this semicircle is going to stop touching the plus end of my battery, and it's going to actually reach this end, which is going to be the negative end of my battery. So as soon as this crosses over to the other side, as soon as my mu becomes tilted this way a little bit, towards downward a little bit, the current changes direction, right? The current will change its direction. Mu, hence, will not be towards this way, but it will flip up. It will switch its direction because the current will switch direction. Now my new current, let me draw that with red, current will switch its direction. Hence, mu will be facing towards this way, not this way, trying to align with the field. It will again rotate the same way rather than making the loop come back to its original position. So every semicircle, the electrodes will switch from, if it was a plus to a minus, from minus to plus, switching my current direction every half cycle, and then that every half cycle, instead of my loop coming back to the same position, it will just keep rotating this clockwise direction for this particular example. So my loop will always go in a circle rather than oscillating if I have this brush system and the electrodes keep changing signs every half cycle. So this is what is happening inside your DC motor. You have a DC power supply rotating your loop constantly within the field. Your other option is to use an AC power source, right? An AC power source will also mean that the current direction here in the loop will constantly change, and every time your current direction changes, your torque direction will switch. So if they are aligned in such a way, every half cycle your current direction automatically changes because it's an AC power supply. Your loop will also keep rotating towards the same direction, in this case clockwise. So it will always go clockwise. One, if you have an AC power supply. Two, if you have this DC motor, which is there in all the battery powered motored items that you might have, like an electric fan that you might hold on your hand, will have this mechanism. Or your battery powered, remote controlled car toy that you have will have this mechanism. Even your car will have this mechanism.